Then for part 2, the horizontal separation of the line of action of the lift and the weight is 0.75 meter. Determine the vertical separation of the line of action of the thrust and the drag. So this is the sketch that I have just now. So if I want to draw it out a little bit more, or if you're not very sure, right, we can refer to the drawing. So if they show us the forces. So actually from this drawing, you can see that the lift and the weight slightly off, correct? Then your thrust and the drag also slightly off. So there will be a distance between these two. So if I draw it out, there will also be a distance between these two forces. From the part 1, we already know that the two pairs of forces, they are equal and to the direction, they are opposite. So this type of forces, when they are parallel, equal and opposite, you know what's the special name given to them? A pair of forces that is parallel and then equal and opposite. Torque is what they produced. So this type of force is called a couple. Yes. And the turning effect produced by the couple is the torque. So the torque produced by the couple are 1 the force times their separation. So this one very easy to understand. If next time you learn driving, have a steering wheel, right? So one hand up, one hand down, so it cause the steering wheel to turn. So similarly to this type of forces, it's always like one up, one down, it will cause it to rotate. One to the left, one to the right, it will cause it to rotate. So in this case, if I look at the weight and the lift, what's the direction of the torque? Clockwise, anti-clockwise? We fling this weight. So it actually will be anti-clockwise. Then how about the drag and thrust? Alright. I heard something clockwise. So if you put it this way, then they'll be clockwise. So if you recall the condition for equilibrium, net force must be 0, correct? And then one more. How about moment? Yep. Actually, from our principle of moment, right? The sum of clockwise moment must equal to the sum of anti-clockwise moment. Make it more general. If we're looking at couples, the clockwise for all the torques, your anti-clockwise and anti-clockwise, you should actually balance out. So then there will be no net torque or no net moments for the system. So if you go back to part 2, this is actually the one we are finding. So torque generated by the lift weight couple should equal to the torque generated by the thrust drag couple. For the lift weight, their separation is 0.75. Then for the thrust drag, their D is unknown. So we can actually equate them. So the formula, F times D. 1 the force times the separation. Okay, if you look at part 3, because of the design, so there's still a natural tendency for the nose to actually tilt downwards. So then to balance it, how does the stabilizer assist? So if I want that it's actually tilt downwards, then the stabilizer will put at the back. Then we can tilt it back from the other side, correct? So stabilizer, right, it can actually produce a downward force. So in this case here, it's not just about like actually moving downwards, but the tubing actually causes it to actually rotate in the anti-clockwise direction. So stabilizer, right, in order to balance it, we can actually create the turning effect in the opposite direction. So hence it can actually produce a downward force, hence there will be a clockwise movement balance out. The what part? So lift equal to the weight, the drag equal to the thrust. Yes. Meaning that it's actually not ascending or descending. So maintaining its height. So thing is that if you want to go higher, then you need to have an upward force, correct? Net outward force. If it's actually going lower, then you need to have a net downward force. So compared to actually our car usually traveling in a horizontal road. So for the planes, right, if they need to maintain the same height, you need to make sure that the forces is not, the vertical forces are balanced. Okay. For part B, yes. Oh, no worry, no need to, like, if you haven't finished copying everything, later at the end, right, there'll be a QR code that you can actually download. So there'll be like all these workings inside the answer key itself. Okay, so for part B, right, this will be the part that I say that I'll be using the new version, like the newer version of your F net equal to dp dt. So just now we said that we have the two versions, F net equal to MA and your F net equal to V dm dt. And this part of the question, I think, is a good demo of like how to use this law. So when our air enters the engine at the initial speed, then it comes up with the final speed. There is a change in their speed. So by using our Newton's law of motion, explain how the air is able to exert a forward thrust on the engine. So if when the air goes in, right, there is an increase in the speed. So it means that change in the speed and mass times V, there will be a change in the momentum, correct? So this is a change in the momentum for the air. So according to Newton's second law, what must be happening to the air? What caused the momentum to trust? What caused the momentum to change? So if you're looking at the Newton's second law, the rate of change in momentum is proportional to the resultant force acting on it. So in other words, right, if a body experiences a change in momentum, there must be a resultant force acting on it. So our air right now, when there's a change in the speed, there's a change in its momentum. So therefore, there must be a resultant force acting on the air. And the thing is that this is air mass, then what's it got to do with my engine? And then must think, then who's the one that exerting this force on the air? The air is sucked into the engine, and the engine push it out with a greater speed, correct? So yes, who's the body? So who's the one that exerting the force? Yeah, but the question first. So which body is exerting this force on the air? It's okay. Yes, just the engine. I mean, it's obvious, but yeah. the body is actually the engine. Because the air goes in, the engine push it, correct? So that's why the engine is the one that exert this net force on the air. Okay, why I want to keep asking this question now? Although you feel that it's quite obvious, right? Because this one brings us to our Newton's third law. Newton's third law is action-reaction. In action-reaction, there's always a body A, body B. A exerts a force on B. B will exert an equal and opposite force on A. So when you're using third law, you always need to state your A and B. And here our A and B is air and engine, correct? So we already just analyzed it that, okay, the air experiences a change in momentum, the engine exerts a force on the air. So by Newton's third law, the air will exert an equal and opposite force on the engine. So that's actually how I put everything together. Your air actually gains momentum when it passes through the jet engine, and hence by your Newton's second law, there's a force acting on the air by the jet engine. And hence by my Newton's third law, engine exerts force on air, air will exert an equal and opposite force on the engine. So there's an equal and opposite force acting on the engine to move the engine forward. So this is the thrust. So the difficult part for this question is that a lot of students can see that the forces there is a force, but you can't really quite see the bodies. That's why when you're answering, you will be like missing certain parts. So if you actually going a little bit and sort out the bodies, right? Yeah. So you can see that engine exerts a force on air, and therefore air exerts the force back on the engine. Then your logic will be very clear already. Second law, third law.
Yes.
Technically, we don't really need to state or like define. No, actually this one is not stating. This one actually is more like describing the force already. Yeah. So the thing I think the question asked is that would there be a mark rewarded for stating the law itself, right? Usually I think the one rewarded is more like you put it in the context of the questions. That's why in this case I said equal and opposite actually link to the forward. Because the engine exerts backward, then the air exerts the forward. And then answer the question directly. That's why the key is really, but that's a very good question. Because like the thing is, the point is, don't just happily go and stick your Newton's law. No, you're not getting marked. You must put in the context, like here. Put in the context, answer the question directly. Then you can get the mark. Okay. There's really a shift in this trend because last time there are a lot of like recalling concept, writing definition, and all that. But then nowadays is that you just do that no mark. They don't want students to regurgitate. Yeah. They're looking more and more of like, are you understanding your question? Are you answering your question? Are you answering your questions? So yeah. Okay. So you see here, the mass flow rate of the air that entered the jet is 210 kg per second. So this is the one that we are saying just now, the dt. And the increase in speed is 580. So this is actually the change in speed. Hence, will give you the change in momentum. So to calculate the thrust, so the force on the jet by the air is equal to the force on the air by the jet engine. So then we can use the rate of change of momentum. So here's the one that the change in the velocity times your dm dt. So the change in the velocity times our mass flow rate. Yeah. The modulus in this case, we're just looking at the magnitude. That's why you see that I need to put the positive or negative. Yeah. But they put a modulus here because technically it should be one positive, one negative. So the two forces, technically they are not equal, but the magnitudes are equal. So in reality, the actual thrust on the engine is different from the value calculated in 2. Suggests a possible physics-related reason for the difference. Let me hear some of the answers. This is more like the open-ended. So in exam, right, anything that is logical, reasonable, and we can get mark. Yeah, anyone want to try? Make sure it's class, that was your answer. Really? No one has tried. No, you have written something. I saw it. What do you have? Changing momentum. Changing momentum is greater possible. So you may need to elaborate on that one. Yeah, but the momentum, what momentum, which one change? Is a mass change or is a velocity change? You don't know. Okay, but actually it's actually linked to one of the possible answers. So yeah, that's why I say that's actually good, but I need to elaborate a bit. Any other answers? We have the air here, we have the engine here. That's why I'm going to think about what are the factors that can be affected. Possible also, right? In reality, it's not very hard to control the density and the mass, right? Yeah, so then that can be different. And what else? Our aircraft is also burning fuels. So it means that it will also be the change in its own mass. And those fuel being burned, right, it is also being ejected. May also cause some changes in the momentum as well. Okay. Those are aircraft or your rockets and all that, right? In real life, right, it's very, very complicated because at the same time, they're also burning their fuels. Then those hot gases come out. That may also lead to, similar analysis we do just now, correct? That can actually add on to the thrust as well. Okay. So I see all these possible ones. Then they'll be wasting your time because point marking, right? Technically it's point marking. So that means even if you give a wrong one, right, you will not be penalized. Yeah. But again, technically you will not be penalized. But some teacher they really do penalize. The field is conceptually wrong. Yeah. Okay. Okay, if you guys are okay, let's move on. So this table actually is more like some of the common forces we considered for free body diagrams. Then our Newton's third law, which kind of go through it in just now the example already. So like the key really is your two bodies, body A and body B. Then you can actually, when you explain it right, also looking at about the two bodies and the directions, forward and the opposite force. So in the last big portion of our dynamics, right, momentum, we just want to talk about momentum already. So the last big group of questions that will come up for dynamics, collisions. We have the bodies that is colliding with each other, then there will be a change in their momentum. So that is where we talk about the conservation of linear momentums. And our impulse we're looking at collision, right? We're also looking at the conservation of momentum versus conservation of kinetic energy. Okay, so that's why it's important to look at what are the type of collision we're looking at. Elastic versus inelastic. Your principle of conservation of linear momentum is applicable for everything. It means that you will always be able to use this formula. Your MAUA plus MBUV equal to MAVA plus MBUV. But only for elastic, the total KE is conserved. And this formula, unless the question really asks you to show that the KE, then you calculate the KE, then you show that the KE is conserved. Otherwise, this formula usually we seldom use it. Too long already. And use it to form a simultaneous equation with another one, right? You'll go quite, complicated. But this one got square. So that's why instead of using this one, usually for conservation of KE, we use the second one. Your relative speed of approach equal to relative speed of separation. So guys, what do you think is a common mistake that student will make when using these two formulas? The number one that will kill you in this question. Direction. Positive, negative. Yeah. So although we are looking at everything is plus plus and all that, correct? And this one is minus. When we sum in, right, all of them, of your V and your P, right, they are all vectors. So when you sub in, you should always sub with their respective positive or negative sign, considering their directions. Yeah. So that will be the challenging part. Make sure all the directions are correct. And later when you calculate, so although sometimes, right, you can assume it's positive, but then later you get answer is negative, it's fine. It just means that it's in the negative direction. But when we are subbing in the values, we are doing the calculation, your positive and negative must always be very clearly defined and clearly subbing. Otherwise, everything will mess up. Everything will be gone. Okay. Okay. So let's take a look at the MCQ question 4. So similarly, if you also highlight the key variables, we have a stationary pin and we have bowling ball. Its mass is 5 times the pin. So the pin speed immediately after collision is 3.33. So they're asking for the speed of the bowling ball before the collision. And of course, right, key information, you also tell you this is a head-on elastic. So you can use both equations. Conservation of momentum and your conservation of KE. So the relative speed of approach equal to relative speed of separation. So if you put it together, so the bowling ball, if you like the mass, so the mass, right, okay, a bit confusing. They never say anything about the values. But again, the relationship, the mass of the bowling ball is 5 times the mass of the pin. So the ball, I put it as 5m, and the pin, I put it as m. And then the initial speed. Pin is unknown, sorry, the ball is unknown, and then the pin is stationary, that means it's 0. And then the V, the final speed. Technically, the ball is also unknown. We also never know that. What is the speed? Okay, then the pin after that is 3.33. Okay, so I think in this case, if we form the two equations, so this one be 1 and then this one be 2. So we'll have 5m u1 plus m2 0. Then we will get 5m v1 plus m 3.33. So in this case, all the n can cancel out. So 5u1 should equal to 5v1 plus 3.33. That will be my equation number 1. The second one, if you use the elastic correlation, u1 minus u2 equal to v2 minus v1. So again, u1 don't know, u2 is 0. V2 is 3.33, and then V1 is also don't know. So U1 should be 3.33 minus V1. Okay, if you want to practice on math, you can solve your simultaneous equation. If you don't like to practice on math, you can use your calculator to solve the simultaneous. Okay. If you're using a calculator, so 5u1 minus 5v1 equal to 3.33, equation number 1. The other one, u1 plus v1 equal to 3.33. That's equation number 2. So you can use our calculator, then you go to simultaneous equation, you key in the values. So you'll be able to get your u1 1.998 and your v1 1.332. So we're looking at the speed of the bowling ball before the collision. So it means we're looking at u1. So therefore, the answer will be 1.998, round off 2.00. Okay.
It's about elastic is equal to just elastic to each other.
Correct. But we need to solve, okay, in the questions, right, actually they will always say we will head on. And that's actually the condition for all the questions that we discussed in our syllabus. So head on is like this, correct? As compared to sideway. Yeah. Sideway, then it will also be like different, and the analysis will be whole different already. Okay, so now let's have a 5 minutes break, stretch, get some water. Then if you want, there are some snacks. If you need to use the washroom, it's over there as well. So we come back, we'll continue with gravitation. And if you've got any questions you're trying to ask me, you can also ask me now. Those online as well. If you've got any burning questions, please let me know. Yes.
You need to introduce the concept.
Actually, we're adding, and in this case, we're adding because it's not so normal contact force balance out the W to sign that. So then again, there is.
Okay.
So in some question, they will ask you to calculate the N one.
So you need to like that, you need to find what's
Correct. So sometimes like if I make it more complicated, right, we can actually give you from N from W, they can actually go and ask you for the value for N, the normal contact force.
Okay.
Yeah. Oh, so because of this, right, the natural tendency.
I got like one like because you right, then it will adjust according to how that you go. That's why it is.
Most of the CG should be covered within diagram, right? The CG and the CP, so the CG is actually the center of gravity, that's where the fluid is acting on. Okay, whereas the leaf bucket and the CP is the center of gravity. Yeah. So because of that, actually this will be the clockwise movement. That's why the tendency will tilt downwards. Yeah, and what you're saying is correct. In the flights, right, if you're going up, down, this thing may change. What if this one we didn't change it that much? So that means its clockwise movement may not be able to adjust it. Then your stabilizer, it can come in to provide the additional downward force. Then it can give you additional clockwise movement. So you are not very clear about the front part, the piece. You actually count the aircraft to tilt downwards, so you have some extra anti-clockwise moment of balance. So then they say the stabilizer can help maintain the equilibrium. They must be able to provide the clockwise moment balance.
So you mentioned that the field will provide an extra clockwise moment that will also add on top of the original clockwise moment.
Yeah, we already have. We try to actually counter for it. Additional clockwise moment to balance the anti-clockwise moment. Yeah, that's why this is answering the question directly. I didn't bring too much of the context. Right?
Thank you. Oh yeah, That's okay. I thought you looked on the like I thought you were so like besides other than here. Not saying her, I don't know how we can make it also bring to the next. Of course, I remember for a little while. It doesn't say it's
Guys, please don't take my foolscap paper. Okay, the foolscap paper back is later after the course. You'll be doing your feedback form, then you'll get your foolscap. Now don't take. But everyone will have a foolscap paper back. After the whole lesson, there will be a feedback form. After you finish it, then you can get a foolscap. So then I'll say that, okay, you'll do it for me. I'll check. Take moments about the intersection between the weights. Oh, so Kathy, right, for this question here, because we are looking at, because the two forces, right, the weight and the thrust. It's not the weight and the thrust though. So you can see for these questions, right, this one is actually the couple. The lift and the weight is a couple. So the couple is actually acting in opposite direction, so they will create a turning effect. So we calculate the torque by the couple, right, is take the force and the distance between them. Then the thrust and the drag is another couple. That's also take the force and then the separation between them. Okay, so this is not like the taking the moment, just force times the perpendicular distance. This is actually finding the torque, the turning effect of a couple, the two forces. So you can think about it as like the combined moment of that two forces together. Okay, we shall continue with our gravitational field. Okay, so traditionally, your gravitational field and your oscillation, these are both. Okay, so yeah, traditionally your gravitation and oscillation both are very big topic, meaning you'll definitely see one question, one big long questions. Yes, for more or for your prelim. Okay, and they're kind of heavy because like you have a lot more concepts and formula. So that's why the trick I'm going to teach you guys, compartmentalized. Break down your one chapter into tiny chapters. Okay. Then when you're looking at your questions, right, identify which portion, then which concept and formulas you'll be using for the part. In one question, right, you'll be many parts, but each part usually will only testing for one concept or two or a few. That means that, but you'll still be coming from a certain session. Meaning, for GQ, right, in this question here, this part is talking about forces. The thing actually will be just calculating forces and all that. Then the second part will be about energy. So usually they will not like this part, then energy, potential energy, and then this one is forces. So you're like, hey, which one should I use? But you see it's very clearly. Part one, forces. Part two, energy. Then you should actually use the correct formula for each part and don't get confused. Okay. So G field, right? Yeah. So actually I will categorize it into, I'll break it down into three parts. So first part, everything about force. So your two formula for force, one, the force between the two masses, then you break it up, gravitational field strength. So the force of a unit mass at a point in a gravitational field. So this is quite clear. So your first formula comes from your Newton's law of gravitation. This is the one that actually if you state, you get marks. We still have the one that you're stating definition and recalling will have marks. So yeah, this one is the one of it. So if you're not sure which are the ones, right? Whenever you can actually go back and refer to your lecture notes. So most of JC in your school lecture notes, in front you always have a learning outcome. And your learning outcome, if you see the keywords, right? State blah 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 blah, recall blah blah blah. Those are the ones that in exam they can ask you, they can give you 1 mark or 2 mark. So state Newton's law of gravitation. State first law of thermodynamics. Something like that. Then you will be given, and this actually I would like to call the 3 marks. 3 marks are because you recall, you memorize, then you regurgitate, you get the mark already. Okay. So for Newton's law of gravitation, you get formula F equal to GMM over R squared. Okay, so if you generalize it, gravitational field, the region of space around a bigger mass, where you place a small mass, you experience a force. So generalize it, right? We're looking at the force acting per unit mass placed at that point. That's why this will become the force per unit mass. So only have 1 M, the big M. Both are forces and force they are vectors. So hence we can look at them like vectors. We can look at the net force, the net gravitational field at the point. Yeah. So you can see the questions are, so from the very beginning, recalling, from very basic, I give you value, then you start being and calculate. Then the more complicated ones, you got the G field from between Earth and the Moon, correct? So at the point here, you have the gravitational field strength from the Earth, gravitational field strength from the Moon. How do I find the resultant? Vectors. That's why we need to look at the net force, which is the net force per unit mass. So this need to consider direction. Okay, so the diagram. So you GM over R squared, that's why it is, so you see the outside is a ratio of 1 over X squared graph. So on the inside, bonus. On the inside of the mass, right, is actually directly proportional. As the radius increase, the G will actually increase. This one here is additional one. It is actually not in the syllabus. If you actually try to define it, you'll be able to derive it. Yeah, but in short, I mean the deriving is also not very important. I think they're not required. So you can just remember the relationship is a straight line. So if you're okay. So what's the level number 4 for forces? Level number 4, we'll start to link this force to something else. So if you're looking at our field strength and your acceleration of free fall. So recap, free fall, the only force acting on the mass is the weight. So if the weight is the only force, then F net will equal to the gravitational force. So we're looking at it, F net is MA, and my gravitational force, actually I can look at it as mg, mass times gravitational field strength, and therefore my A will equal to G. So the acceleration, the A here, right, is what we call the acceleration of free fall, and the G here is your gravitational field strength. So this is actually one of the showing questions that they actually tested. How do you show that when the object is free fall, its acceleration of free fall is equal to the gravitational field strength in magnitude? Okay, put everything in formula, but whatever things that actually we are saying just now, we can actually translate into words. So that will give you the explanation mark. Then the second part, right, if we link it with the other forces. Our Earth is not stationary, it is actually rotating about its axis. So because of that, right, everything on the Earth, actually currently we're all undergoing circular motion. So if you undergo circular motion, what is required? Let's remember, let's recall what's required for object to undergo circular motion. Yes. Yes, then what about centripetal force? Oh, common question. Is centripetal force a new force? Yes. So actually everything is still back to Newton's second law. So when it's actually rotating, right, it's a constant change in the velocity. So that means the object is still accelerating. So it's still accelerating, so you still need a resultant force. It's just that this force, right, this resultant force, instead of causing it to accelerate, because of the 90-degree, the force is always 90-degree to the direction of velocity. Hence, it will cause it to constantly change direction. So if we put in here, right, then what is the resultant force then? To undergo circular motion, we need to have a resultant force. How do we get the resultant force? If the object just experiences a gravitational force, then yeah, then this one can provide the centripetal force. But right now we are standing on the Earth. Is there any other forces acting on us? As we learned from secondary school, right? Whenever something resting on the surfaces, there are always two forces, right? Yes.
Normal.
Yeah, normal contact. If I draw anything here, there will always be the W and there will always be a N. It's just that last time we learned is that right now, this calculator, if you rest it like that, these two forces will be equal and opposite, and hence F net is 0, correct? So now, if you zoom up and look at this same thing, same block over here, the N and your W, actually, they cannot equal to each other. In fact, they will always be, so if we are rotating together with the Earth, these two forces will always be slightly different, so that it can give us a resultant force, so that this resultant force can act as the centripetal force to allow us to rotate together with the Earth. So our resultant force here is your Fg minus T. Or if you're looking at something that's resting, right, your resultant force here is Fg minus N. So then this Fr here is the one that providing the centripetal force. So then if you use this value, right, so in the lab or in the experiment and all that, we're not measuring the weight. So if you're using a scale, use a normal bathroom scale, right, we are actually measuring the normal contact force. If you're using the spring balance, we are measuring the tension. So hence this tool that we actually measured, it will be slightly lesser, slightly smaller than your actual weight. Then this value we calculate, right, is actually, so this T and the N is what we call the apparent weight. So then if I let this equal to mg, then this G here, right, is known as the apparent. So this G calculated is not the actual gravitational field strength. It's actually the apparent field strength. The next question, do you think that this FR will be the same in all the location, let me say in any location on the Earth?
Any location.
Yeah, will it be the same like here in Singapore versus somewhere in Alaska or somewhere in US or somewhere in Africa? Why? Different gravitational field strengths, the main different value for the actual G? That can be one reason. Okay. But let's assume that the Earth is a perfect sphere. Everything is the same, also uniform density and all that. Then G is the same everywhere. Then do you think that this FR will be the same everywhere? Still shaking. Why? Mm-hmm. Correct. So he has a very good point. So if you are looking at here, this is my circle, correct? So my radius is actually this big. But let's say you are somewhere higher up. You go to Iceland already. Then Iceland here, we are still rotating about the blue axis in the middle. You can see that the R here is much smaller. Compared to all the way, if you are standing right at the North Pole. So technically, if you go and find that spot where it's actually rotating against, right, your R becomes 0 already. If your radius becomes 0, and our centripetal force, right, is, let's say we use mv squared over r. Actually, let me not use this one. Let me use mr omega squared. So when your r becomes 0, right, the resultant force, the centripetal force becomes 0 already. So at the pole here, your Fr equal to Fg minus T. These two actually will equal already. So then the T I'm measuring actually will be the true gravitational force already. Compared to at the equator, you see your R is actually the largest. So then your T measured will have the greatest deviation. Okay. Everyone okay? Okay. So second part of this chapter about the energy, gravitational potential energy, and gravitational potential. Compared to your forces, right, these are all the scalars. And again, a refreshed version of your GPE. Your GPE is not MGH anymore already. So please don't use MGH for this chapter. Use MGH. The teacher will not look at the answer already. You'll just mark wrong for everything. And trust me, there are really people doing MGH. Yeah, and still using 9.81 for your G. Okay. Whenever it's actually slightly further and all that already, your G is not constant already. And hence we cannot use MGH. So MGH is only applicable when it's near the surface of the Earth, where your G is approximately constant. But let's say I bring you to the moon already. Your gravitational field strength confirmed is not 9.81, correct? Yep. That's why I don't use that. Okay, the formula for gravitational field strength and the derivations. Easiest way to understand it is, we always define it as the work done by the external force, correct? Without a change in the velocity. So in this case, if there's no change in the velocity, so guys, is there any change in the KE? No, right? But there's work done. So work done, conservation of energy. If there's work done on the system, this work done must be converted to something. So if it's not converted to KE, it'll be converted to the other form of energy, the common one, mechanical, is potential energy. Yeah. So that's why in this case here, the work done will be all converted to potential energy. And because I start at infinity, I take it as 0. That's why this work done will just equal to the final PE at the spot. So that's actually how we get the whole definition and the derivation for the formula. So interesting part and also question. So why your gravitational potential energy is always negative? Yes. And then don't know already. So actually still go back to the derivation we're saying just now. PE equal to work done, correct? Work done equal to force times distance. So in your WEP chapter, work energy power, there's a special case you can have negative work done. What's the special case? Yes. Yes, the force and your displacement is opposite. Although your work done is a scalar, but the rare case where the force and the displacement are in opposite direction, the work done by this force is actually negative. It's a negative work done. Means that it's actually taking away energy from the system rather than adding on to it. So in this case here also, because our gravitational force is attractive. So in order not to change the speed, your external force must be pointing away. It's pointing away, but your displacement, this is your F net, but your displacement is going towards. So these two are in opposite direction, and hence the work done by the F net is negative. based on what we discussed just now. So that's why in your definition, in your explanation, the first point you may mention, yep, your gravitational force is attractive. Then this will be your second point you mentioned. And hence your F net and the displacement move will always be in opposite direction. And the work done by the F net, so this will be the third point. Your work done by your F net, which is your U, will always be negative. So the 3 points that we used to explain why it's always negative. Okay. A potential is just the energy per unit mass. So now let's take a look at the MCQ 8 and 9, as well as our question 3. So this one here, right, if you actually work out to have an object of a mass m, it falls freely from at rest at x and hit the surface of the earth. So at the beginning, right, the distance is actually 5r from the center of the earth, and of course when it hits, okay, this one is 5r. When it hits it, this one is not like 0 already. When it hits it, the distance actually become r. So in this case, we can actually find out what's the change in gravitational potential. So initial is, using the formula, negative gm over r. And then our final negative gm over r. So then if you work it out, so the answer will be negative 4/5 gm over r. Yeah. Part B.
What is it about?
They're asking which one is false.
For my bed.
Yeah. That's why this one, right, if you work it out just now, it's actually negative 1 plus 1/5, correct? So it's actually equal to negative 4/5. So this one actually is wrong because it's missing the negative. And it makes sense actually going closer towards the earth, correct? It should be losing GPE. Yeah. So B will actually be correct. The decrease in GPE, right, will actually go to the opposite of the work done by the field. Again, because we are looking at the definition just now, you see F net is in the opposite direction, but FG will be in the same direction. So therefore, the work done by your FG moving towards the earth, right, will actually be positive. That's why this one is correct. Okay, part D, this one you're also using the formula. So use your gravitational field strength, G is gm over r squared. And then this one can actually calculate. and find what's the difference. So then the speed of impact, change in GPE equal to change in KE. So same thing, this one, you can also work out the expression. So should we look at the correct one also. That's why the only thing that is not true is your A, because of the missing negative sign. You guys want, you can take a picture of this one. Yeah. Then at home, if you have time, right, you can go and work up the expressions. Yes, picture time, picture time.
So the closer you are to the surface, the more GPE you have.
The lesser
Take a
GPE, the lesser, so it become more negative. And infinity is 0.
Yeah.
Then we go closer to the mesh, right, it become more and more negative. That's why it become lesser and lesser.
It's counterintuitive.
Hmm?
It's counterintuitive.
Correct, because the magnitude is actually increasing, but because it's negative. So the more negative actually means that it's getting smaller and smaller. And question 9, the two sites are considered for a rocket launch. A is at the equator, whereas B is nearer to the North Pole. Taking the Earth to be a uniform sphere, which of the following statement is true? So this one here, right, we're looking at the escape speed. So we actually don't need to look at the rotation and all that in this case here. We just need to look at the change in the energy. Okay, we'll actually cover more in the details later. Yeah, for the escape speed. But all in all, in order for you to escape, right, you must have enough energy to actually send it to infinity. And because of that, both sides, if we consider as a uniform sphere, radius will be the same, gravitational potential will be the same, hence will be the same amount of energy needed. Okay. Yeah, I'll show you guys the longer explanation. As long as it's uniform, right? Your GPE at any point, the potential at any point will be the same. But back to the point that we mentioned just now that Earth actually is not a perfect sphere, and density is also not the same everywhere. And therefore, right, the field strength or like gravitational potential at any point on the Earth actually is different. Yeah, that would be like some of the questions they were asking for that. Okay, so I think now I will cover the rest of the concept for G-field. Then we'll move on to our FRQ question 3. So after we cover the front part, right, the forces, energy, and potentials, usually you can see that the question they are quite separated, either testing just forces or just testing on the energy and potential. So the last part is like the one that more like application. You're putting the energy, you're also putting the forces into place. And say that this one, we're looking at two types. One, we're looking at the forces required for something to orbit. So these are looking at satellite, we're looking at the moon, we're looking at even those kind of questions, the binary star. When the two stars, they are actually undergo circular motion about a common center of mass. Okay, so in this case here, we're looking at the gravitational force acting as centripetal force. Second type of application question is the escape speed. This one consider about how to send an object from whatever point in the gravitational field to infinity. Then this one we are looking at more the, just now is more on forces, correct? This one is more on energy. how much energy is needed? Then it's because we've got negative GPE, you need to provide the positive KE to overcome it. Okay, the first one, our satellites. For this one here, the useful relationship, your Kepler's third law. P square proportional to R cube. Should we see the detailed derivation? You'll be this whole part over here. Okay. Then for the second part, for our escape velocity. So I said escape velocity, this one. So you can see right for the satellite here, satellite motions, we'll focus more on the force. Meaning Fg provides Fc. Your gravitational force provides the centripetal force needed for the circular motion for the satellites. So this part over here, for the orbiting spacecraft and satellites, the Fc is provided by the gravitational attraction. Then whereas for the escape velocity, we're looking at the change in energy. So for you to escape, right, you must be able to reach infinity, theoretically. So therefore, the gain in GPE is basically your 0 minus the initial GPE. Hence it's GMM over R. So if this gain in GPE is equal to the loss in KE, yep. So if you let the half mv square equal to GMM over R, this is actually how we get the expression. Again, so if you look at the derivation, so yep, we're basically sending it to infinity, right? So therefore, we're looking at the change in the energy. And infinity here, okay, PE, KE. This one minimally will be 0. This one minimally will become 0 also. And then at the start here, this one will be negative GMM over R. And this one here will be half mv squared. That's why from here to here, there's an increase. But from the initial KE to the final KE, right, there must be a loss. So that's why minimally, the minimum amount of energy is basically the minimum KE needed for the GPE to increase. Okay. So if we're looking at our satellites, and we're considering the energy of the satellite, so same thing, we can look at the GPE, KE, and the total energy. So GPE, this one will just go by the formula. Whereas for KE, right, this one we can go by the derivation. So same thing, if I start off right where is Fg provides Fc. So Fg equal to Fc. But because now I'm looking at the kinetic energy, so it's V. So I use mv square over R. So from the derivation, so actually I can get this. So guys, the trick to remember, if you already memorize your EP, and you take a look at this one, the back is exactly the same. All you need to do is add the front half. You see that? GPE basically is negative GMM over R. KE basically is also GML over R, but half. So you add the two together, your total energy, GPE plus KE. Basically, right, the back is the same, GMM over R. And the front, you have -1 plus half. So -1 plus half, you got, sorry, -1. You got -half. That's why, right, the expression for the three of them, right, very, very similar. It's all GML over R, GML over R, GML over R. It's just the coefficient is different. -1, half, and -half. Okay. In MCQ, you don't need to derive this whole thing, you can just use it to calculate. Yeah. Okay. For the last portion, geostationary. This one is a special type of satellite. In that case, that the special feature is that it always remain at the fixed position relative to any point on the Earth. So in order to do that, right, the condition is that it must be rotating at the same speed. It must be rotating on the same Earth, same direction as the Earth. So the orbit period must be the same. The direction of orbit must also be the same. And the last thing, very importantly, must also lie above the equator. So this is actually all explained here already. If it's above the equator, right, you can see that this plane here, it will intersect with the center of the Earth. So your FG is always pointed towards the center. But if we actually leave it out to a higher altitude, right? Sorry, the higher latitude over here, it still need to tilt towards the center, but the whole plane will actually be tilted already. So then sometimes you will actually be circling on top, then later you go to the bottom. That's why you'll be overing the two hemispheres.
The geostationary orbits we have a smart output.
No, you can do it for the other planets and all that. So one of the TYS question, right, they actually put it on the Jupiter.
What are the definition given for us?
Relative to the Earth's surface. So then that means that, but you can still generalize it. That means you can still use it for other planets or the moon. That's the one that they tested very often, right? They really liked Jupiter. Yeah, it's quite a few questions on Jupiter. And then there's a moon that is going geostationary. Okay. Okay, so now let's go to the question number 3 of the free response questions. But again, no need to copy down. Same thing, I will send you the answer key later. Show you guys the answer key later. Okay, but I said this one will be one of the commonly tested questions. So why gravitational potential? Why gravitational potential energy is always negative? So I said the 3 points. 1, your FG is always attractive. Therefore, your external force and the displacement is always in opposite direction. Therefore, point number 3. Point number 3. What done by this force, and by definition, your GPE is always negative. That's why the 3 points. Okay, for part B, this one shows how does your gravitational potential from the surface of a planet varies with a distance r from the center of the planet. And okay, in this question now, they specifically say that a planet. They never say Earth already. So please don't assume it's Earth. I know some of you are very hardworking, you go memorize the mass of the Earth. then go and use it then for calculation and all that. But if they never say it's Earth, and if the question actually never give the mass of the Earth, you're not supposed to use it. Yeah, so don't go and very hardworking, memorize it and then use it, then it's not wrong. Yeah. Okay. So the moon orbits the planets. The mass of the moon is much, is orbit radius, our R is 1.0 times 10 to the power 6 km. Calculate the orbit speed. So here, if you want to calculate the orbit speed, right? So this one is about your satellites. Satellite forces. Forces, F3 provides FC. So your GMM over R square will equal to MV square over R. The thing is that if you look at the information, we don't really have a lot, correct? All we have is the, what do we have? We have the mass of the moon, we have the orbit radius, but we don't have the mass of the planet. We don't have, we don't have the mass of the planet. So if we look at the expression, GMM over R square equal to MV square over R. Okay, I can cancel out this. Right? At the same time, I can also cancel out the M. Okay, so actually what we have is left hand side GM over R, right hand side V square. So GM over R looks familiar, right? Potential negative GM over R. Yeah. And since I already have the distance already, and previously it shows how does the gravitational potential change with distance. So therefore, I should go back to the previous page. Look at the distance, 1.07 times 10 to the power 6 km. What is the potential? Should we go back here? Okay, but the axis slightly different now, so we need to do some conversion. So 1.06 times 10 to the power of 6 km. If I change it to meter, it's 9. This is 8. So let me take out 1 0. So it's actually 10.7 times 10 to the power 8. So I shall go to 10.7. Okay, 1, 2, 3, 4, 5. That's 11. 10.7. So 2, 4, 6. So 7 is over here. Then you can draw it down. So this is your 10.7. Yeah. Use your graph, use your ruler. You can find the value for your potential. Yep. So from the graph, right, the value is about negative 1.2 times 10 to the power 8. So this one, right, is GM over R is equal to V squared. So if I want to find my V, you just need to take square root 1.2 times 10 to the power 8. Again, working wise, right, why I do 2? The one is the longer one, which if I need to use the value, I'll use the longer one. Then your final answer, you just round off to the significant figure required in the question. Okay. Then from here, if I want to find the total energy of the moon, right? Technically, from the potential times the mass, so that will give you a GPE already. And then since I already have the speed, KE, I can use half mv squared, correct? Of course, this is like the long one. So if you want to calculate it, correct? So of course, the short one, if you are familiar with your expression, you can also directly use the negative half G over R. This one will be using the shortcut. But the problem with this one is that sometimes for structural questions, right, if you never derive it and it's nowhere, we need to recall it, a bit risky. The teacher may say, but how do you get this formula? In this case, you can just go by the normal one. So total energy will be potential energy plus kinetic energy. So potential energy mass times potential. Kinetic energy half mv squared. Then just submit already. Submit the value, they will get negative 8.88 times 10 to the power of 30. Okay, so if you look at the next part. So we have the rod projected upwards with a speed 45 km per second from the surface of the planet. So if we ignore the resistive force, show with clear looking that the rod will not escape the planet. So escape velocity, we must look at the change in the energy. In the sense, change in GPE must equal to the change in KE, correct? I mean, with the V, we can calculate how much KE you have, correct? Then you must look at how much GPE is actually needed. So the surface, the R is 0.7 times 10 to the power 8. So you can find the initial potential at the surface of the planet. So looking at the conservation energy, the K initial, GP initial should equal to the KE final and your GP final. Yeah, so if this working right, at the time that when it actually come to a stop, your KE becomes 0 already. So let's calculate what's this value. If later I'll get a positive value for my potential, means that, oh, it's able to reach the infinity and beyond. Yep. But if you get a negative, means that it's still somewhere stuck inside the gravitational field. Should we stop in and then we'll work out? No, sadly you get a negative value. So it means that by the time that you use up all its KE, right, its gravitational potential is still negative. Should you ever escape yet? Also can. But later for part 2, you realize why we actually do this one instead. Part 2, the maximum distance. Yeah. So technically this one will be the maximum distance, correct? So this is at the furthest you can go already. This is the point that where your KE becomes 0, and this is the potential. Yeah. So if I already know the potential at that point, and we have the graph, so you can actually use the graph to actually look back to find what is the distance. just putting these two together, right? Just now I have a very good question is that for part one, can I use at infinity, your PE is 0. So go and find what is the change in PE, and hence I find what is the change in KE. And then I can find the V escape. So use this method also can. Okay, but then the thing is that then for second part, right, I need to calculate everything again already. That's why the other way is that, okay, so we can also consider that the changed conservation of energy. The initial amount of total energy should go to the final amount of energy, correct? So the maximum speed, sorry, the maximum distance, the furthest you can go is always when your V becomes 0. It's like throwing up a rock. The highest point is when it come to a stop, correct? So we can actually use that. Then we can calculate what is the potential. Then we compare this potential, see whether it's equal to 0 or not. Yeah. That's why it's actually linked to the second part. Then you say that, okay, this method is actually better. So then I can find the potential, final potential. Then I can actually use the graph to actually, your figure 4.1, to actually find the maximum distance. All right. There's another short 5 minutes break. We'll come back. We'll continue with oscillation and going through the rest of the question. Okay, so in this 5 minutes, right, if you can take a look at the mock exam papers. I'm going to show the answer for the MCQ first, so you can actually mark your MCQ. So then later we'll go through the question right a bit faster. So you can just focus on the one that you all need help with.
Actually, is the value for index on the base, so they actually will have more.
Yeah, so usually for like even for Earth, right, like the mass, the radius, and the not memorize.
Which is given.
Yeah, so you need to use it. The question will give you. If the question never give you, means that you're not supposed to use it and memorize it. You need to have some way to actually work it out from the data given.
Okay.
Yeah, it will be like this one. They give you the graph. You just actually read it, read the GMM, read the GMM out on the graph.
Let's say the long question. We just need to look at the points.
You don't need to read the passage first. Actually, go with the pattern. So you kind of like scan through the question, right? Like what this question is about. Then you go back to the passage. Then you see the relevant ones. So you usually have to do back and forth. So that in this one, then this is relevant. They highlight the data and the informations. Then this question, then this relevant. They highlight. Like better focus. Then you'll be reading faster also. Okay.
Speed of approach, speed separation, 3.33. I thought it was things come to I thought they should have find this.
It's still the formula. It's still the U1 minus U2 equal to V2 minus V1. Because of that, right, we got two unknowns already. Yeah, two unknown, your U1 and your V1. That's why you need another equation to solve for unknowns.
Also, let's say the object is moving, but at the same time the object stays moving. So you need to identify that as a space where it's in.
If it's a position, right, you see the thing is actually stationary.
You didn't need to be the student here.
Yeah, or you got our friend who is doing here. Yeah.
Weekday.
Hmm?
Weekday.
No, it's free now. Yeah.
Now do I sign up for that back? Maybe if I use person.
Okay, this place is usually open for the overmugged students. That's why I mean that I think that the study launch, yeah. That's why if you are coming, right, you need to be a student here. Or like I said, the other one is that your friend will be a lot. You study here together.
For me, tuition fee per month is about how much?
Tuition fee per month, you can actually find it on the website. I think at the rate, each lesson is, if I remember correctly. Yeah.
This. Then they told me the next day will start. Each vessel will have a short dwelling. So it's yeah. Exactly. Over this.
Hey. Okay, for the last part for oscillation. Oscillation. The one you got a lot of formulas and things to memorize. We start with a simple harmonic motion, the definitions, then all these terms and the formulas. Okay. The definition for simple harmonic motion, and more importantly, the defining equation. Your A is equal to negative omega square x. The other one over here, the relationship between V and your displacement. Okay. So guys, right, first one, as well as the definition, this one need to memorize. Because they will test you, they will ask you to actually show it, then if you know what's a definition, it'll be hard to show. Okay, so the key, right, actually there are two parts. One, your A directly proportional to X. Then two, the negative sign means that A and X are in opposite direction. So in your showing question is also these two. You need to show that value-wise, acceleration is directly proportional to displacement. Then direction-wise, acceleration and displacement are always in opposite direction. Okay, the second one I put right for the V, that one no need to memorize because it's given in your formula list. So actually you just need to use it. And from here, right, actually one good use, also no need to memorize. One good use of this one is to find what's the maximum, what's your V naught. Maximum, if you look at the formula, if my X becomes 0, then the inside the square root become X naught square, correct? So your maximum V is actually equal to omega X naught. This happens when X equal to 0. So this is the additional one you can actually kind of like deduce from this formula. And which is quite useful. Also, a lot of times actually they really love to ask what's the maximum speed, what's the maximum velocity. So if you have trouble like memorizing or like deriving, then you can actually use this formula. Okay, then from these two, the two graphs, A against X and your V against X. So always these two shapes. Straight line, negative gradient, and whereas our V is a ellipse. And the question you'll see, right, like your question 10 here, very straightforward type of question. So I already have my A changing with my X. So right now, when you have a period of oscillation, that's twice than before. So which line could be produced? So you got to think that, okay, the shape will still be the same, but when the period change, right, how we're going to change is gradient. So what's the gradient for this one? A equal to negative omega square x. So hence the gradient is omega squared, the negative sign, correct? So when our period is twice, how will it affect omega? And then think, which formula? When our period is double, how will our omega change? So again, formula. What's the formula linking T and omega? Or we call it W. Which formula? To say. Yep, omega equal to 2 pi over T. So that's why, right, if your period double, your omega actually will be half. So if my omega half, then omega square actually will become 1/4. So that means that for this graph, right, the shape will be the same, but the gradient will become 1/4. You're looking at your answer, which one give you 1/4? So the answer is actually D. But over here, if you look at the last value, instead of -4, so now it left is only -1, so it become 1/4 already. So again, I think let's divide it. So for simple harmonic, right, the first portion is about the definition, so showing that it's a simple harmonic motion, and also looking at the forces to find out what is the value for your omega and all that. So sometimes the question will give you, they can just use it to calculate your omega and your calculations. But sometimes that they will give you like a free body diagram, like the spring that is going up. So this one will be the one that you actually need to derive to find what is your F net and how is your net linked to your X. Like for example, in this one here, your F net is actually negative Kx. That's why we get MA equal to negative Kx, and your A will be negative K over MX. So you satisfied the two conditions already. A directly proportional to X, and the negative sign shows that they are in opposite direction. Okay. So then next, so next two parts, right, for simple harmonic motion, one will actually focus on the kinematics. So here, actually, we are looking at how does our displacement, velocity, and acceleration change with time. And here is actually all you have is all the trigo functions already. Yeah. So actually, we're mapping over a sine function or cosine function. So guys, what's the difference between these two? Which one should I use? If when your t equal to 0, x equal to 0, you use a sine function. Why? If you sketch your shape, your sine function start at 0. Then if when your x equal to x naught, when t equal to 0, then we change to a cosine function. Same thing, we'll look at this point. When your t equal to 0, your x is at maximum. So then the other one, we can just use differentiation to get the expressions. So the next question, so when do we use all this? What type of question will require us to use all these functions? 1. The very direct one, they will ask you at t equal to blah 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 values, what is x, v, or a? This one is just direct calculation. So you just identify the functions, then you submit the value for the time. This one you can calculate the value of displacement, velocity, or a. So it's more straightforward calculation type of question. Second type, this one more common in MCQ, to find the sine. So this is the one that, example, I have a v against x graph, then I give you this random point p here. Then I ask you, this is my a against t. Then I give you some random points like here, 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 or here, a, b, c, d. Which point is corresponding to your p? So this will be the types of MCQ that will be given. And actually, we'll also be using these type of functions. Yep, have you guys seen this kind of question before? So the key to this kind of questions, right, is always first identify what's the one that's given. So for this one, right, for our point P here, you can see that your x is positive and your v is also positive. So therefore, if I'm looking at if you're looking at my a against d graph, if my x is positive, that means that my a is positive or negative. Whenever you got a and x, this one's straightforward. This one don't need to think about functions. This one you can just use the relationship. A equal to negative omega square x. So if x is positive, that means that a opposite direction, it must be this. Can you guess? Yes, negative. Yes, it's correct. Hello? So actually, we are looking at a point that I have negative acceleration, correct? So that means this one cannot. This one cannot. Then out of the other two, which one? Then I'm looking at if my v is positive, then what's my a? Which point will be my a? Then this is where you need to use the function already. My a right now, right, is actually a sine function, correct? What will be my function for my v? Cosine. Sure. Like testing everyone's trigo. How do I get v from a? We must do integration, right? So if you integrate sine, what do you get? Negative cosine. Are you missing a negative sign? Yeah. Differentiate cosine, we got negative sign. That's why when you integrate, put back. So your v will be a negative cosine. So negative cosine, if I sketch it over this graph, you'll start off with here, and you go up, then you go to the maximum, and then you go down, and you go to the minimum. Okay? So you look at this point here. This point, your v will be positive. Whereas for this point, your v is over here will be negative. V positive. And this point here, your v will be negative. And which point we are looking for? We're looking for a positive v, correct? So that means that this one here will be our correct answer. This will be like the second type of questions that we actually can use this stuff we can use like all these functions to help us determine like which are the corresponding points. So the trick is always to actually sketch. Okay, if you find the function of the other quantity, right, you sketch it over and make sure all your points are matching. Then you check which one will actually give you the one that you want. Okay, so the energy. Similarly, we're looking at the energy, how it changed with time, and also the energy, how it changed with displacement. I think this one should be okay. Then the last portion for your simple harmonic for oscillation, we're looking at damped oscillation and versus the forced oscillation. So for our damping, right, basically we're looking at the system will lose energy until it will come to stop. So that this is due to a presence of the resistive force. So based on the amount of forces, right, we can have a light damping, we can have a critical damping, and we can have a heavy damping. And the amount of forces is that, so the first one, light damping, the force is very small. That's why it will only cause the energy to dissipate over time. So the amplitude will decrease gradually. Period will remain almost the same. Okay, in most of our workings, right, usually period will take it, in when we're sketching, the period will take it the same. Yeah, because at the beginning, this effect is actually quite negligible. Then critical damping is that it doesn't actually oscillate. So you can imagine once it will start, right, the forces will actually cause it to stop at once. So it doesn't oscillate, and then you will return to the equilibrium position in the shortest possible. But if I keep on increasing these forces, then you actually start to take longer already. You take a longer time to return. Then the last one for the force oscillation and the resonance. So force oscillation is that previously is that we actually displace it, then we just let it go by itself. Whereas for force oscillation, you have an external driving force. So this will cause the system to oscillate at the frequency of the driver. So the driver is constantly transferring the energy, and hence this one you will, even there is a damping force, right? You will not be able to, you actually will be able to go on a bit longer. So when we actually match the driver frequency and the frequency of the system itself, right? This is where we have resonance. Maximum transfer energy that cause the oscillator to oscillate at the maximum amplitude. And that's why the keywords for resonance is always the maximum amplitude. And the driving frequency matches the natural frequency of the oscillator. So the effect on damping. We have a damping force, it will still take away the energy, and hence the degree of damping will cause all the amplitude to decrease. And we can look at the graph. As the degree of damping increase, the peak will shift to the left. And then also all your amplitude will decrease. Okay, so now I'll go through the question 11, and then we'll go through the rest of the mock exam paper. So a figure actually shows the variation of your frequency with your amplitude of a force oscillation. So system is then now object. So this system now is subject to another periodic driving force, as shown in your figure B. What is the frequency that the system will oscillate with? So recap, if you have a force oscillation, the system will oscillate at a frequency of option number 1, natural frequency. Option number 2, the driver frequency. Which one? We go with its own frequency or we go with the driver's frequency? Yes. From notes, you will follow the driver. You actually go with the driver, so you will be following the driver frequency. Then how do we find the driver frequency? Driver frequency is shown in your figure B already. That's why don't get confused by your figure A. To look at your second one. So driver frequency, this is my force. And you can see this is 1 period. Then this will be the second period already. So it means that my 1 period T is 2.0 second. Therefore, my driving frequency 1/T. 0.50. Yeah. No, that one is just there to confuse you. This one shows that the variation of the frequency changes. Yeah. So actually, what we can deduce, right? This is your resonance. So your 3 hertz is actually the resonance. That means it's the natural frequency of the system. But the question is not asking for the natural frequency. It's asking for the frequency that you oscillate with. That's why it should be the same as the driver. Okay, so then for the rest of the question, right? So this is the MCQ. So if you it passed through. So guys, you check your answer first. Let me know which actually you go. Okay, let's go back to the beginning. Okay, we'll just go by page. So if you need the explanation or if we go through, then let me know. Otherwise, I'll just run through already. Then later we'll focus more on the 2 long structured questions. Yes, question 1, question 2, anyone? Nope. Question 1. Question 2. Okay. So we're looking at the SI base unit for this little symbol over here. So you need to look at the rest already because your unit of our mu here should equal to the unit of the other 3. So if I let this one be the unit of E, unit of M, and the unit of the top. Then we actually look at it one by one. So what does each one of them? So E is the charged on the electron, correct? So what's the unit, SI unit for charge? Coulomb. And then M is the mass, so it's kg. Then this little thing top here is actually the average time between the collisions. So it means it's second. Okay. But the thing is that we want SI base unit, so Coulomb cannot. Coulomb cannot. Okay, so then we need to think away. How do we change Coulomb to SI base unit? Correct. Current is charge per unit time, right? So Q is IT. So Coulomb should be ampere times second. So if I do ampere second over kg times second. So I've got ampere second square kg to the power of -1. Then question 2 on your kinematics. If a cannonball launched at the angle theta above the horizontal. So this is my u and this is my theta. And its initial KE is E. So initial KE, right? So let me this E here, this formula, half mv squared. So if we let the initial velocity is u, so it's half mu squared. What is the KE of the cannonball at the top? So you reach the top, right? Your Vy will become 0 already, correct? So left is only your Vx. And if you assume air resistance is negligible, your Vx should equal to Ux. How do I find my Ux? If we resolve our velocity, correct, should be u cosine theta. So this will be my velocity at the top. If I use it to calculate KE, half mv squared, so half m u cosine theta squared. So I will express it out. Half mu squared times cosine square theta. Now you see half nu squared. That's your initial E already. That's why it will be E cosine square theta. Okay, next page. Okay, 3 and 4 will go through already. Okay, question 5 and question 6. 5. Any call for 6? No. Okay. 6 also. Okay. Okay, so this one is actually our process, and this type, okay, my favorite. So this one, right, you should always do as a whole thing, and then after that you divide and conquer. So your free body diagram, right, you can do the whole thing first. So if you do the whole thing, the total mass is 6 kg, correct? So then the only force acting on it is the F over here. Again, smooth surfaces, no friction. My acceleration should be F over 6. Correct? So right now, if I'm looking at what is the force exerted by the 2 kg on the 1 kg mass, meaning this force over here. I'm going to call this one F12. So divide and conquer. If I only care about that force acting on 1 kg, let's just draw out the 1 kg. You have the F that is acting forward, and you have this force from the 2 kg that is acting backwards. It's still accelerating to the right, so it means that F net to the right. So take this direction as positive. Your F net should be F minus F12. And your F net equal to MA. Because I only care about my 1 kg, right? So that means that my mass right now is only the mass of the 1 kg. So it's 1 times the acceleration equal to F minus F12. So A will equal to F minus F12. And as we found out just now, your A is F over 6. So means that F over 6 is F minus F12. So bring it around. The force between the 1 kg and 2 kg should be 5 over 6 F. So then question 6 is more like understand the different terms and then put it together. We have a constant force, then we have a stationary object. This is a frictionless surface. So when you actually push it right, it will cause the object to accelerate uniformly and reach a velocity v in the time t, covering a distance s. Which one is correct expression for the ke of the object at time t? Technically, if I have v, right, I can do half and v square, correct? Or don't have? Then I'll think, I have a force, and this force is acting over a distance. Another way we can think about it, your principle of conservation of energy. So then this is work done is used to increase the ke. That's why work done will be the change in ke. And because our initial ke is 0, stationary, that's why the work done will just equal to the final ke. How do we find what work done? Force times distance. That's why Fs. Yeah. That's one question, right? How come I cannot use FVT? What the new formula you learn for this chapter, right? Power equal to FV. And then energy equal to power times time. How come I cannot do FVT leh? Yes. Your V, right, if you go and calculate it, it will be the power at that moment. But your V actually start from 0 all the way to the final velocity. That's why this one is out. Okay, so move on. Next page. Question 7. Everyone okay? And our question 9. So I go through already. Then we move on to. Okay, so all this will be on the wave and the superposition already. So question 12 and question 13. Yes, anyone? Or haven't tried it? Same question 14. This one is on your stationary wave. Question 13. So question 12, this one is your polarization. I think okay. The last question, right? This one is on your first law of thermodynamics. Does anyone need it? Yes. So for this one, it's a cyclic process, right? So in our first law of thermodynamics, if it's a cycle, right, go back to the same point, there's no change in the state, hence there's no change in the internal energy. So delta U will actually equal to 0. Then by our first law of thermodynamics, delta U is Q plus W. Okay, so Q plus W. Q is the amount of heat transfer to the system, whereas W is the work done work done on the system itself. And one of the point that separate point, work done on the system, if we have a P against V graph, right, it's actually equal to the area under PV graph. And for cyclic process, it will equal to the area enclosed in the cyclic process. So this is a circle ma, so that means this will be the area. So the work done is area of the circle pi r square. Okay, diameter is 2, so it means that the radius is 1. So the work done actually is equal to pi, so it's about 3.14 joule. So the question is that this work done now, we find the area, only find the magnitude. Then how do we know the direction? Is it positive or is it negative? So then you got to check. If it causes the gas to expand, then your W is negative. If it causes the gas to contract, okay, expand meaning V increased, contract meaning V decreased, then your work done is positive. So the overall, right, we always focus on the one on top. Anytime processes, right, it's always like that, this shape, correct? So that means that you always have two arrows. That means that either going out and then coming in, or the other way, going out and coming in on top. So you always look at the one on top. The one on top will have a larger magnitude. That's why the overall will be following this one on top. So this one on top, you can see it's actually going outwards. Going outwards means that the volume is increasing. V increased, so it means that your W is negative. So the work done here should be -3. So 0 will equal to Q plus -3. Therefore, Q should equal to 3, positive. That's why 3 drew into the gas. Okay, let's move on to paper 2. The first one on the kinematics. If you already have the initial velocity, I have the vertical component. So to find our Vx, right, you can use your Pythagoras theorem. Yeah. So your V square should be Vx square plus Vy square. So we can actually use Pythagoras, then we can actually show that your Vx is 3.6. So you leave the ground at t equal to 0, reach the maximum height at 0.49. Sketch separate lines to show the variation with time until the ball returns to the ground, the vertical component, and the horizontal component. So if you're ignoring air resistance, right, your horizontal component will be constant, correct? Whereas for your vertical component, you will have your constant AY equal to G. That means 9.81 downwards. So if you're looking at Vy against time, I should also get a straight line, but it will be a negative going down. So that's why this will be our answer. Vx will be constant, so 3.6 throughout the whole thing. Whereas for our Vy, right, we'll start from the maximum, then at 0.49, it decreases to 0. Then after that, you will go all the way down. So the gradient is negative 9.81. Okay, then to calculate the maximum height reach, we can either use, because we got time already, 4 our time given when it hit the ground should be at 0.49. Okay, I think there's a typo over here. 0.49 seconds. 0.49 seconds. Yeah. So use the formula. At 0.49 seconds, you reach your maximum height. So use S equal to UT plus half AT squared. Then you can find the maximum height is 1.2 meter. Can also. Yeah. Your Vy square equal to Uy square plus 2as. Because at this part, you know that this one will become 0 already. I can show you this one. Okay, then question 2 on your circular motion. We have the speed over here, and then we also have your R is 0.08. So therefore, omega V over R will be 3.00. This one is actually for your rotating dish. The center of the rotating dish has a radius of 8.0. So it's a rotating dish again, that's why you can use the value back. This will be confusing because you have the center that's rotating dish, and then you also have the bob, should also be undergo circular motion. So determine the tension in the string for theta equal to 30. So if you're looking at the string, right? Okay, two things are. So this will be the tension, and then that will be the weight of the bob. So if we resolve it also, this will be t cosine theta, where this will be t sine theta, correct? Particularly, right, if it's actually going around, there's no change in its height. These two forces should balance out each other. Okay, whereas the horizontal, nothing to balance it, correct? So this will be your F net, which actually provides your centripetal force. Should I put it all in? If you just focus on the vertical component, our t cosine theta will equal to mg. Sorry, this one workings. Sine 30 degree, cosine 30 degree. So t cosine 30 degree will equal to the weight. Yep, so then we work it out. We can find the tension should be 16.991, should go to 17 Newton to SF. So if you want to calculate D, right? The horizontal component provides the centripetal force. So our T sine theta, I got a lot of double sign, will equal to our MR omega squared. So the tricky part is that, what is my radius for the circular motion? We'll go back to the diagram again now. Our radius should be from the center. That means that all the way here. So this portion is your D. Then this portion is the unknown part. The string we already have the length. This is 25.0 cm. And the angle just now I give us 30 degree. So it means that for this portion below, how do we find it? How do I find this little part over here? Yep, Tokaso. Opposite over hypotenuse. So I mean this is my sine. Can that be x? So sine 30 degree is x over 0.25. So it means that my x is 0.25 times sine 30 degree. So hence my radius will be, my radius big R should be the t plus x. That's why your d plus 0.25 sine 30 degree. Okay. It's rotating together with a rotating dish, so that omega is the same. So it's still using the 3.00. To be able to find the value for d, so it will be 0.50. So as your angular velocity increases, right, your theta will increases, but you will always be smaller than 90. The moment it becomes 90 degree, right, you see it become horizontal, correct? If your tension is horizontal, but there's still a weight. So that's why it cannot be horizontal. If it's horizontal, then there won't be anything that's vertical to support the weight already. So tension actually need to have an upward vertical component to keep it in the vertical equilibrium. That's why the string cannot be horizontal and must be smaller than 90 degree. Yes. Generally valid. It is not generally valid. The displacement can be no, cannot. This one you need to look at the forces. Yeah. What to say, you see if it's actually higher than that, then that component even downwards. So that downwards and the weight, there's nothing to balance it. It will cause it to come down already. Yeah. Okay. Okay, so now let me show you guys this one first. The answer key. So please scan and you can download the answer key. So whatever things you're copying, haven't copied yet, no worry, it's all there already for the structural questions.